the first topic that we want to deal with this term is how chemical reactions exchange energy with their surrounding environment. And this is a bigger field of chemistry, which is called thermochemistry. And thermochemistry principles are used to measure the types of energy changes you get in any chemical reaction, but they're particularly relevant to chemical reactions that absorb or release a lot of heat. So for instance, if you're interested in the amount of available energy that you can store in a solar cell, or the amount of energy that you can release by burning, say, 500 pounds of gasoline, thermochemistry provides the framework by which we can measure possible sources of energy and make determinations like what types of fuel sources are going to be most cost effective and most efficient to power our entire society. So while it may seem like we're extremely focused on the nitty-gritty of how specific chemical reactions release energy in these kind of weird archaic terms like specific heat and enthalpy in this reaction, all the skills that we're building in this chapter are geared toward allowing you to make quantitative number-based predictions about how much energy is available in different types of chemical sources of energy. And every chance we get, we're going to tie back the skills that we're learning here towards bigger societal issues like how we harvest, store, and transfer energy from one place to another. So the example that I want to put in your mind in terms of how a chemical reaction releases energy is a very dramatic example, which is known as the Thermite reaction. On paper, the Thermite reaction is a very kind of boring looking written chemical reaction, which says that 1 mole of iron 3 oxide in the solid state reacts with 2 moles of metallic aluminum in the solid state to give us 1 mole of aluminum oxide in the solid state and 2 moles of iron in the solid state. So in terms of the physical picture of this reaction, you can imagine that this reaction starts with rust and solid pieces of aluminum. So the shavings from an old bicycle frame would do. On paper, this doesn't look like a particularly dramatic reaction. In fact, it looks pretty boring. But this reaction releases a lot of energy in the form of heat. In fact, thermite is used in welding and demolition. And with a good amount of thermite, you can actually easily melt all the way through a car's engine block or any solid piece of iron. This is obviously a demonstration that it is not safe to try at home unless you've had very specialized training, but to just give you an idea of how important understanding energy changes are to how we can use chemical reactions to transfer or store energy, the thermite reaction makes for a dramatic example. And on the page below, I've included a link to a video where you see some cool demonstrations with thermite for demolition purposes on an old car. The question that we're going to be concerned with in this chapter is, why does the reaction release such a massive amount of heat? And what's the connection between the energy of the bonds in the reactants and the energy of the bonds in the products that allows this reaction to release this massive amount of heat? So I'd recommend you pause the video here, and if you haven't checked out the YouTube video that's linked below, check out that thermite demonstration, and then come back and we'll continue the introduction. All right, so what we want to do first in this discussion is build up our basic toolkit so that we can understand where we are in talking about the energy released by a chemical reaction, what's the relationship between energy and heat, how is energy measured, and this will allow us to keep our bearings when we're dealing with some of these kinds of difficult word problems and laboratory measurements that involve a lot of specialized terminology and mathematical calculations that all have simple formulas associated with them, but choosing the right tool for the job is very important. So it's particularly important in this chapter to be able to keep your bearings and understand the relationships between like energy and heat and temperature, how temperature change for an object and the object's mass dictate the amount of heat released, and concepts like this. So the first thing we want to talk about is energy. And from a physics standpoint, chemists use the same definition as physics do. Energy is the capacity to either supply heat or do work. So we're going to see when we measure the energy released or absorbed by a chemical reaction, there's two ways for that energy to be manifest. The release of heat or the absorption of heat by the system, so heat into or out of the system, or what we call work. Work you can think of essentially as expansion or contraction against a constant pressure. So for instance, if you're inflating a bike inner tube with a hand pump, you are doing work forcing air into the inner tube and causing it to inflate against atmospheric pressure. Let's deal with energy first, and then we're going to circle back and talk about how energy relates to the concept of heat and work. So in general, all of the energy in the universe is divided into two basic types. There's kinetic energy, which is the energy associated with any object in motion. And there's potential energy, which is any type of stored energy. So that's all the energy that's not associated with an object in motion. Kinetic energy is nice because you can always calculate the kinetic energy of a moving object as long as you know its mass and the speed it's traveling. So kinetic energy is always calculated as 1/2 times the mass of the object times its velocity, its speed squared. So if I have an object in motion and I know its mass and I know its velocity, I can calculate its kinetic energy. Potential energy is a little more nebulous because potential energy is any type of stored energy. Calculating the potential energy of a system is harder because you need to know all the forces acting on it in order to calculate the total amount of stored energy in the system. So kinetic energy, I think, is pretty easy to visualize. If any object in motion has kinetic energy, and I can calculate the kinetic energy of any object in motion if I know its mass and its velocity, I can calculate the kinetic energy of any object that's moving. That could be a train, that could be a linebacker, that could be a golden retriever who's very excited to bring you the ball back. And if we just look at these three scenarios, it's pretty obvious which of these three objects in motion should have the greatest kinetic energy. The locomotive, the steam locomotive, is generally going to have the greatest kinetic energy because it has the largest mass and it can reach the highest top speed. So largest mass, largest speed, or highest speed, the steam locomotive is going to win in terms of its total kinetic energy versus a football player in motion or a dog in motion. But what's important to remember about kinetic energy is that speed actually counts for more than mass does, because if you're calculating the kinetic energy is based on the mass, but it's multiplied by the speed squared. So if you have two objects with similar masses, but one is moving quite a bit faster than the other, the speed counts for more in determining the kinetic energy. So it may seem counterintuitive, but an NFL linebacker running at top speed trying to make a tackle and a 70-pound dog who's excited you to bring his ball back actually have pretty similar kinetic energies. Even though the NFL linebacker probably weighs about 250 pounds and the dog only weighs 70 pounds, a dog's top speed is around 35 miles per hour, and an NFL linebacker's top speed is around 22 miles per hour. So because the dog can move faster, that actually counts for more, and a dog running at top speed has a very similar kinetic energy to a linebacker running at top speed. That doesn't, however, mean that getting hit by the dog hurts more than getting hit by the linebacker, because impact is something that's more complicated to measure than just kinetic energy. But if you've ever been hit by a dog at top speed, you know that even a medium-sized dog running full tilt into you hurts a lot. Potential energy is harder to calculate because potential energy is any type of stored energy. So if your object is not in motion, but it's about to be set in motion, it has potential energy. And so drawing a bowstring back prior to releasing an arrow is a type of potential energy where the force of your pull is stored in the string and is about to be imparted to the arrow. If you dam up water behind a dam, the water has potential energy, which will turn into kinetic energy when the water starts to move downhill and is released into the spillway. And the potential energy of that water is going to be determined by the height that it sits above the dam, the gravity that's going to pull the water downhill. Whereas for the arrow, The potential energy depends on how far you can pull back the string, how much strength is being stored in that bowstring, and the properties of the bow that are going to go into releasing the arrow. In chemistry, the potential energy that we're most concerned with is the type of potential energy that's stored in chemical bonds. And so remember that chemical bonds, whether you're talking about a covalent bond between a carbon and a hydrogen atom, or an ionic bond where you have two ions held together, there is potential energy in that chemical bond because you have attractive and repulsive forces. The attractive forces being the attraction between the electrons and the protons in the nucleus of the two atoms, and the repulsive forces being the repulsive forces between the electrons and the repulsive forces between the protons and the two nuclei of the atoms. You have repulsive and attractive forces that hold atoms together. And so if you can break that bond or make atoms change bonding partners, that changes the energy of the system because the attractive and repulsive forces in the system change. So when you burn a fuel source like wood or like natural gas, you're breaking bonds in the original fuel source, and the reaction is releasing heat, and all that energy is coming back out of the system and into what we call the surroundings, warming us. So when we talk about potential energy in this chapter, this is the example that we're really going to be interested in, how energy in the form of heat moving from place to place is related to the energy of bonding multiple atoms together. All right, looking at this another way, chemists defined all energy, all the energy in a given system as either energy that is released by doing work or energy that is released by giving off heat. Work is not something that we'll talk a lot about in this chapter, but we're going to circle back to it next chapter when we talk about gases in chapter 8. In physics, work is defined as a force exerted over a distance. So work and energy are closely related concepts in physics and have the same units. When we talk about work, energy, and chemical reactions, we're going to talk about work in the sense of a chemical reaction releases gases in a container, and this causes the container to expand, doing work on its surroundings. So again, you can think of pushing air into a bicycle tire tube or a car inner tube as doing work on a system, because as you're putting more gas into the inner tube, the pressure inside the tube increased and it pushes back more on the atmospheric pressure that's pushing on the outside of the inner tube. So we're going to circle back to work when we talk about gases. We're going to leave it alone for just a minute. And although chemical work is a very important way that a chemical reaction can exchange energy with its surroundings, we're going to focus in this chapter much more on how energy is released in the form of heat in a chemical reaction. And we'll save talking about expansion work and energy for when we talk about gases in the next chapter. So for the rest of this introduction, we're going to focus in on how heat and energy are related. And the first thing you have to have under your belts here is you have to recognize that even though in common language, when we talk about heat and temperature, we mean the same thing. It's hot out here, it's cold out here. We're saying that's a statement about the temperature. From a physics perspective, temperature and heat are not the same thing. So make sure you recognize that when you're learning to work these problems and you're building up your skills in chemistry, that temperature and heat are not the same thing. They're closely related, and we'll see how they're related in a minute, but recognize that temperature is an indirect measure of the total kinetic energy of a particular chemical system, whereas heat is in fact energy itself, and it is energy in transit from a high temperature object to a low temperature object. So the temperature of an object, or the temperature of generically what we're going to call the system, is a measure of the heat that's available or that is associated with that system, but heat and temperature are two different things. Mathematically related, but they're two different things. So the big takeaway, heat does not equal temperature. However, the temperature reflects the kinetic energy of particles in the system. So for instance, you can think of a hot liquid, a liquid with a high temperature, is going to be made up of molecules, or what we just simply call particles. We're talking generically about what makes up a solid, a liquid, or a gas. you're going to have molecules in a hot liquid that are vibrating faster and are in faster motion than the molecules that are in a cold liquid. So the temperature is an indirect measurement of the kinetic energy of the molecules and the particles, the components of that system. And when we talk about energy released by chemical reactions, you're going to see in this chapter that we're obsessed with heat flow. So heat flow is going to be talking about heat energy that goes into an object or heat energy that comes out of an object. And in order to understand the direction that heat is flowing easily and make the math as straightforward as possible, you may not find the math in this chapter to be that straightforward, but it will come with practice. And the first thing we have to do to make the math as straightforward as possible is learn to define two related things that in thermochemistry and physics we call the system and the surroundings. Where the system is going to be where the physical process or the chemical reaction that we're interested in is happening, and the surroundings is everything else. So typically when we're talking about the system, our system is going to be a block of metal, it's going to be a dish with a chemical reaction occurring in it, it's going to be a beaker with a chemical reaction occurring within it, and then the surroundings is everything else in the universe. And so to calculate energy, we're going to see it's very important that we define what is the system and what is the surroundings and where the boundary between the two occurs. Where does the system end? Where do the surroundings begin? And so our typical picture is always going to be, we have a chemical reaction that's happening in a vessel, and we're to call that the system. And then everything else in the universe is going to be the surroundings. So in terms of understanding how heat energy exchanged by a chemical reaction relates to the energy of the bonds that are present in the molecules, we're going to talk a lot about how much heat is flowing into the system or how much heat is flowing out of the system into the surroundings. So this is always going to be our picture where we're talking about a physical thermochemistry experiment. We define the surroundings, we define the system, and we talk about the heat flow into the system, or we talk about the heat flow out of the system. And when we're looking at a chemical reaction, we are an observer. We are in the surroundings. So if a system feels hot, if you're heating up a beaker on a hot plate, you put your hand on the beaker and the beaker is warm, well, the beaker is the system and you are in the surroundings. So if the system feels hot and you're in the surroundings, that means heat is coming out of the system. If the system feels cold, that means it's actually taking heat energy away from you when you touch it. And that means heat is flowing into the system. So in terms of keeping your bearings in these thermochemistry problems, one of the key things that I want you to remember is if the system feels hot, that means heat is coming out. If the system feels cold, that means heat is flowing into the system. And in thermochemistry, we have special terms for both these scenarios. We classify the energy change in a reaction partially by defining whether heat is absorbed, going into, or released, heat is coming out of a chemical system. And we abbreviate the heat flow simply with the lowercase letter q. By convention, we say that if heat flows into the system, we say that the system feels cold, Q is positive. If the heat flows out of the system, the system feels hot to the touch for us, Q is negative. So the sign of the heat flow determines whether heat is being absorbed or heat is being released by the system. And we're going to see that from a chemistry standpoint, we have another set of names that we can give this scenario. If Q is positive, the system feels cold to the touch, we call that an endothermic reaction. The reaction is absorbing heat. And if the heat is flowing out of the system, the Q is negative, we refer to that as an exothermic reaction. The reaction is releasing heat, the system is releasing heat to the surroundings. So what we have here are essentially three ways of saying the same thing. If heat flows into the system, we call that an endothermic process. And that means that the Q is a positive number. If heat is flowing out of the system, we call that an exothermic process, and the Q for the system is negative. So negative Q means feels hot, possibly on fire. Positive Q means feels cold, maybe very cold to the touch. All right, so in this chapter, the way we're going to go about building your toolkit so that you can deal with talking about energy changes in a chemical system and how those energy changes relate to the potential energy source that is the chemical bonds involved in the chemical reaction, is we're going to work to learn to define the relationship between heat, temperature, and energy. We're going to talk about how we can relate heat flow to temperature through a constant called specific heat or heat capacity. We're going to talk about the technique of calorimetry, a basic experimental setup by which a chemist or a physicist measures the heat absorbed or released by the system. We're going to talk about state functions, enthalpy, and the first law of thermodynamics. We're going to learn how the concept of enthalpy relates to heat flow, and then we can start talking about how we relate heat flow to the energy available in chemical bonds through thermochemical equations and Hess's law. There's 4 sections in chapter 9, section 9.1, 9.2, 9.3, 9.4. 9.1 is essentially what we're covering here and in the next lecture, where it talks about an introduction to heat flow and energy. In 9.2, we talk about calorimetry as an experiment. And in 9.3 and 9.4, we relate the heat flow that we measure in a calorimetry experiment to the energy available in the chemical bonds for the molecules that make up the system. The key vocabulary to get to grips with in this chapter we've already got started on, but again, the big things are to recognize the relationship between heat and energy. Heat is a type of energy, but heat is not the same as temperature. The concept of a state function is going to turn out to be big. That's a mathematical concept that we're going to introduce. And we're going to talk a lot about the relationship between what we call the heat of the reaction, or the enthalpy delta H, versus the heat flow Q. So this is kind of the framework for the chapter. Meet me back here in a minute where we're going to start talking about the units of energy and how we use simple equations to relate the temperature change of a sample to the amount of heat absorbed or released by the sample. And I'll see you back here in a minute.